Okay, so now we'll be talking about an isolated spherical conductor. An isolated spherical conductor of radius r is shown like this. Before this, I need to remind you that any conductor must be equipotential. That means that no electric field inside the conductor. So let's say now you are given an isolated spherical conductor. You know that it is equipotential. That means the potential is constant throughout the volume of the spherical conductor. And then the potential is given by this Q over 4 pi epsilon naught R, where the R is the radius of the conductor. And then when the distance is larger or equal to R, then the electric potential starts to fall. So that means that the V is inversely proportional to R when R is greater or equal to capital R. Still remember the formula electric field equal to negative dV over dr. By using this formula, you can get these two expressions for the electric field. That is, when you differentiate this, you know that this is a constant. You differentiate a constant, you will get 0. And then dV dr, if you differentiate this one, then you will get negative Q over 4 pi epsilon naught R squared. Since there's a negative sign here, then you will get E equal to Q over 4 pi epsilon naught R squared. Okay, so you know that inside the conductor, the potential is a constant and then the electric field is 0. And then outside the conductor, the potential falls. And then the outside the conductor, the electric field will also fall, and then it falls more sharply than this because it is inversely proportional to R squared. So it will definitely fall more sharply than this. If you want to consider the electric field in the x direction, then of course this will be negative, because in this region, the electric field is pointing to the negative x direction. Actually, there's one more thing I want to add on. Let's say if there's really electric field inside the conductor now, that means the electric field will accelerate the free electrons in the conductor and there will be a current. But then this is what chapter? This is the chapter of electrostatics. Do you really expect to see any word current in this chapter? Of course no. So you have to remember that inside an isolated conductor, the electric field must be 0 so that the free electrons will not be accelerated, so that there will be no current inside the conductor. Because if there is any current in the conductor, that is already in another chapter. Alright, let's do a question. A metal sphere of radius 3 cm, which is the capital R, carries a charge of negative 12 microcoulomb. Please determine the electric field strength at a point of 5 cm from the center of the sphere. Okay, so now you know that small r is larger than r, so you have to use this formula and also this formula. Okay, so may I know the electric field strength at this position? You use this expression to solve for the problem. Then when r is greater than r, you use the formula of this one to find the electric potential. And then Please sketch the graph of the potential V against distance from the center of the sphere, and sketch also the graph of electric field strength against R. So you know that because this is negatively charged, therefore the potential is negative. Okay, just now it is positive because the charge is positively, the conductor is positively charged. Alright, so once again, the electric field inside the conductor must be 0, and then it increases more sharply than this. Okay, because this is V is inversely proportional to R, and then this is E, which is inversely proportional to R squared. So if you want to find out the V at this position, the value would be alright, so this is a constant and this is the value of this. Okay, which shows the correct electric field lines when a neutral spherical conductor is in a uniform electric field. First, you need to remember that inside a conductor, do we even have electric field? No, we cannot have electric field inside the conductor because the conductor is an equipotential body. Okay, so now this is automatically out. Okay, next, we should remember that when the electric field is approaching the conductor, it will approaching it at a right angle. That means that it must be right angle to the surface of the conductor. And then do you think this is possible? It means that the field will point towards the conductor. No, this is not possible because this is a neutral conductor. Only when this conductor is negatively charged, then maybe there's a possibility of this occurs. But then since this is a neutral one, definitely this is wrong. Okay, so we need that whatever field comes in, it will definitely comes out later. Spherical conductor Y is larger than the spherical conductor X. Y is larger than X. Now, initially, conductor X is uncharged, whereas conductor Y is charged. A wire is then connected from conductor Y to X. Which statement is true when equilibrium is attained? First of all, they are conductors. And then the wire itself is also a conductor. Therefore, 3 of them are all conductors. When they are all conductors, just now you learned that a conductor must be an equipotential body. Therefore, conductors X and Y have same electric potential. So this is correct. Okay, now I want to prove to you that Qy is larger than Qx. That means that the charge of Y must be larger than charge of X. But then I really need a numerical value so that I can prove this more easily. So let's now assume that this is twice larger than this. Okay, we assume Ry is 2Rx. So you know that potential of Y is equal to potential of X, and then you use this formula. And then you realize that the 4 pi epsilon naught can be cancelled out. Qy over Ry equal to Qx over Rx. So when the Ry is larger than Rx, when Ry is larger than Rx, Qy is larger than Qx. So I realized that, okay, the charge contained by the bigger conductor must be more than the charge contained by the smaller conductor. Okay, conductors X and Y have same surface charge densities. Okay, surface charge densities is equal to the total charge on the surface divided by the total surface area of the surface. So for the conductor Y is like this. Just now when I say that Ry is 2Rx, then Qy should be 2Qx. So you substitute Ry equal to 2Rx and then Qy equal to 2Qx. And then you realize that the surface charge density of Y is this. Now, you find the surface charge density of conductor X, and then you realize that the surface charge densities of X is twice the surface charge densities of Y. So you know that the smaller conductor will have a higher surface charge density. Next, conductors X and Y have same electric field strength at their surface. Okay, you need to find out the electric field on this surface, which is Ey. Okay, so Ey equal to Qy over 4 pi epsilon 0 Ry squared, and then you substitute Qy equal to 2Qx, Ry equal to 2Rx, and then you can find this expression. Then you do the same for the electric field at the surface of the conductor X, which is here. So you realize that the electric field on the surface of the conductor X must be twice the electric field at the surface of conductor Y. So you realize that these three statements are wrong. And in fact, for this statement, I need to give you a more detailed explanation, but definitely not in this video. I want to show you that, okay, let's say this is a conductor, and then somehow you make the shape of the conductor becomes like this. You will realize that actually there will be more surface charges when the surface of the conductors becomes more sharp. That means there will be more surface charges at the edges, and then there will be less surface charge on the flat surface. Alright. Two spherical conductors X and Y are located at a certain distance apart. X is of the radius this and carries a charge of this. Y is of the radius of this and carries a charge of this. Determine the charge which remains on X when X and Y are connected by a wire. Okay? Once again, you know that when they are connected by a wire, the wire and the conductors X and conductors Y, they are all conductors, and therefore the conductors must be an equipotential body. So you know that when they are connected, Vx must be equal to Vy. And then now, you have to remember the principle of charge conservation. That means that the total charge of the whole system before the conductors are being connected by wire is equal to the total charge of the whole system after the conductors are being connected by the wire. Okay, so you know that Qx plus Qy must be equal to this column. Okay, Qx is the charge on the X after they are connected. Qy is the charge on the conductor Y after they are connected. Okay, so by using these two equations, you can solve for Qx and also Qy. Actually, for this chapter, which is the isolated spherical conductor, actually, we also think of this as a capacitor, but then this is in the next chapter, which is capacitor. So I think I will talk about it when it is in the chapter of capacitor. Okay. So in the next video, we will be talking about the motion of a moving charged particle inside a uniform electric field. Thank you.